Hello everyone. Once again, I welcome you to the video lecture on first part of the second module, that is testing and parallel operation of a transformer. In last video, we were discussed about testing on transformer. We discussed polarity test on transformer and Sampner test on transformer. And also we discussed separation of the hysteresis and eddy current losses by the testing of a transformer. In this video, let us discuss the parallel operation of a transformer. What is the need for parallel operation on transformer? So, we'll quote many points regarding the necessity of parallel operation. The first point is what? The increased load. You know, the load demand it go on increases nowadays. If the load demand increases, it cannot fulfill the with the existing transformer. So since we will go for the increased, we'll go for the parallel operation. That is when load is increased and it exceeds the capacity of existing transformer. Another transformer may be connected in parallel with the existing transformer to supply the increased load. Second point is non-availability of a large transformer. In order to fulfill the increased load, so we need the larger capacity transformer. If larger capacity transformer is not available, in that case, we'll consider the smaller rating transformers. So such type of transformers can be connected with the parallel condition. So will fulfill the whatever be the increased load. That is non-availability of large transformer. If a large transformer is not available, which can meet the total requirement of load, two or more small transformers can be connected in parallel to increase the capacity. Next point is increased reliability. You know, if multiple transformers are running in parallel, if any fault occur in one transformer, then the other parallel transformers still continue to serve the load. That means if number of transformers are connected parallelly, in that case, if any one transformer is under fault condition, in that case, the remaining transformers will continue to serve the load. So this is what the increased reliability. This is one advantage that we go for what the parallel operation of a transformer. The next point is transportation is easier for small transformers. If we go for the smaller rating transformers, so its transportation is what? It is easier. If installation site is located far away, then transportation of the larger transformer is very difficult. In that case, we'll consider the smaller rating transformers so that are connected in parallel in order to meet the what? The required load demand or required capacity. So this is what the diagram represents the parallel operation of transformer. So here the two transformers are connected parallelly. So this is one transformer, this is one more transformer. So here both the transformer, the primary which is connected to the source bus bar, and both transformer secondary it is connected to the what? The load. Both are common. So both transformer primary is connected to the what? Common source bus bar, and both secondary are connected to the what? The common load. So here also shown. So this is what transformer A, this is the transformer B. So the primary winding of both are connected with what? The common supply bus, and here the secondary of both the transformers are connected to the what? The common load. Next, conditions for parallel operation. So when we go for the parallel operation on transformer, so there should be a conditions in order to go for what? Parallel operation. Either it may be what single phase transformer or it may be what the three phase transformer. So let us see what are the conditions for parallel operation. So first we'll consider the single phase transformer. So the supply system voltage and frequency must suit the primary windings of a transformer. So this is a first condition on single phase transformer parallel operation. That means the supply voltage and frequency, it must be fulfill the primary winding of a transformer, both primary winding of a transformer. Second point is the transformers that are connected in parallel must have same polarity. Both the transformers must have the same polarity. Either it may be the additive polarity or it may be subtractive polarity. So this polarity test on transformer discussed in previous video. Third point is the voltage ratios of primaries and secondaries of transformers must be same. If you consider number of transformers are connected in parallel, so all transformers, the voltage ratios of primary and secondaries must be same. You know the voltage ratio, this is what with respect to primary and secondary voltage. So this ratio, it represents the what? Voltage ratio. Next point, the percentage impedances should be equal in magnitude and have same X by R ratio. You know the percentage impedance of the both the transformers magnitude should be same, or X, both the transformer X by R ratio should be what? Same. You know X by R ratio means what? X means what? The reactance, R means what? The resistance. Obviously the winding has the both the parameters. So if you consider the transformer A, let us consider transformer A, transformer B are connected in parallel. The transformer A X by ratio should match with the transformer B X by R ratio. That means both the transformer X by R ratio should be what? This is same. Next point, if the transformers have the different kVA ratings, the equivalent impedance should be inversely proportional to individual kVA rating. If the transformers have the different kVA ratings, if suppose consider transformer A and transformer B are connected parallelly, so transformer A has some kVA rating, transformer B has some kVA rating, but both kVA ratings are different. In that case, we can also consider the parallel operation for such transformer, but the condition it should fulfill that the equivalent impedance should be inversely proportional to individual kVA rating. So if you consider the transformer A equivalent, that is transformer A, if you consider that kVA rating, it should, sorry, transformer A, you just consider transformer B, you just consider both are connected parallelly. So here the equivalent impedance of both the transformers should be inversely proportional to the what? Individual kVA rating. For example, the kVA rating of the transformer A is what? 5 kVA. The kVA rating of transformer B is what? 2 kVA. In that case, if you consider the equivalent impedance of the system, it should be inversely proportional to the individual kVA rating. Either it may be what? 5 kVA rating transformer, or it may be what 2 kVA rating transformer. So this is one more condition it should fulfill in order to go for what the parallel operation of a transformer. This is for what single phase transformer. Now for three phase transformer, what are the conditions? So that we'll discuss now. So here also the transformer should have the same polarity. Either it may be additive or it may be what subtractive. Next point, the relative phase displacement on the secondary side of the three-phase transformer to be connected in parallel must be 0. So obviously, three-phase connection means what? So there will be a what? The phase displacement we can observe on secondary side. So those phase displacement on the secondary side, if you consider, so both the transformer phase displacement should be what this is what different. So if I consider the phase displacement of the transformer A is 30 degree phase displacement, or you can say that phase shift. So next we'll go for what transformer B phase shift is what minus 30 degree. In that case, we just consider the difference in that. So that is 30 minus 30. So that will become what it is 0. So this is the meaning. The relative phase displacement on the secondary sides of the three-phase transformer to be connected in parallel must be 0. So next point is the line voltage ratio of the transformers must be same. You know the line voltage? So obviously the either it may be star connected or it may be delta connected. So if you consider the line voltage ratio of the both the transformers must be what same. This is one more condition you should fulfill. Next point, the ratio of equivalent leakage reactance to equivalent resistance should be same for all the transformers. That is, the ratio of equivalent leakage reactance to equivalent resistance should be same for all the transformers. Again, it is what the X by R ratio. That is, X by R ratio of the both the transformers should be what same. So that we discussed in single phase transformer. Same here also, X by R ratio of the both the transformers are what same. So next point is what the transformer should have equal per unit leakage impedance. So that is both transformers leakage impedance should be what equal. That is per unit leakage impedance is what equal. So next point is what the phase sequence must be the same and no phase difference must exist between the voltage of the two transformers. Again here the phase sequence must be the same. Either it may be what 30 degree phase shift. So another transformer should also have the what same phase shift, and this phase sequences are same. Either it may be R, Y, B. So these are the phase sequences. So again you consider the one more transformer phase sequence, that is R, Y, B. That means so each phase sequence it is connected to the what the respective phase sequence. So those phase sequences are what same, and no phase difference must exist between the voltages of the two transformers. If you consider transformer A and transformer B, the transformer A has some voltage, secondary voltage, and transformer B has some secondary voltage. Either it may be line voltage or phase voltage. And there should be no phase difference between what these two, transformer A voltage and transformer B voltage. So these are the conditions you should fulfill in order to go for what the parallel operation of a transformer. Either it may be what single phase transformer or it may be what the three phase transformer. So here some points will go to common. So that is the polarity of both the transformers should be what same, and ratings are same, X by R ratios are same, and leakage impedances are same. So these some points are what is same as what a single phase transformer and a three phase transformer. So some points like what the phase sequence, phase displacement, then phase shift point. So these will consider only for what the three phase transformer parallel operation. Okay, this is what the condition for parallel operation of transformer, either single phase transformer or three phase transformer. Now, what are the condition we discussed? So that condition either these conditions will fulfill or not. So that will check here. Now let us consider the circuit diagram of two single phase transformer. A and B are connected parallelly. So let us consider this is the transformer A and a transformer B. So both the transformers are connected in parallel in such a way that the both transformer primaries are connected with the common supply of voltage rating V1 and both transformer secondaries are connected with the common load of voltage rating of what V suffix L, and both transformer has the what some turn ratio. So some points are mentioned here. So that is the transformer A current, transformer B secondary current, and load current and load voltage and impedance. So here we'll consider, let us consider A1 is the turn ratio of transformer A, A2 is the turn ratio of transformer B, Z suffix A is the equivalent impedance of the transformer A referred to secondary. Z suffix B is the equivalent impedance of the transformer B referred to secondary. Z suffix L is the load impedance across the secondary. I suffix A is the current supplied to the load by the secondary of a transformer A. I suffix B is the current supplied to the load by the secondary of the transformer B. Then V suffix L is the secondary load voltage and I suffix L is the what? Load current. So these all parameters are mentioned in the what? Circuit diagram. Now by considering the circuit diagram, so here we used to what to define the conditions. So we just check the conditions are satisfied or not. These are the what in general conditions. Okay, so now by the circuit diagram, so here, so applying Kirchhoff's current law, so here we'll apply the Kirchhoff's current law at this node. So we'll apply the Kirchhoff's current law. According to the Kirchhoff's current law, you know, so this load current, so load current is the what, the sum of the what, the secondary winding current of transformer A and transformer B respectively. So since we can represent IA plus IB is equals to IR, just refer this circuit diagram. See the secondaries of both the transformers are connected parallelly means, so whatever be the current we can obtain at the load terminal or load side, so we'll get the summation of these two current of the transformers which are connected in parallel. IA be the what? The current which is the secondary current of what? Transformer A. IB be the what? The secondary current of a transformer B. Then load current will be what? The combination of what? These two currents. Call this as equation number 1. Now apply the Kirchhoff's voltage law. So for both the transformers, so let us consider transformer A. So if I apply the Kirchhoff's voltage law for the transformer A secondary side, then we'll get PL is equals to VA by A1 minus IA ZA. See here, this is the VL voltage. So this VL voltage will be what? The voltage across this winding minus voltage across the what? So this impedance. You know, voltage across this impedance is what? IA into ZA, and voltage across this winding is what? VA divided by A1. So these two difference it gives what? The load voltage. since I can represent VL is equals to VA by A1 minus IA into ZA. Similarly, if I consider the transformer B at transformer B circuit, so here also this VL voltage will be the difference in the voltage drop across the secondary winding of transformer B and voltage drop across the water, the impedance. So call this as equation number 3. Now here I just consider equation number 3. So in equation number 3 I just consider, so in place of IB I substitute here IL minus IA. So here I just remove IB outside, this becomes IL minus IA. So this IB value will be substituted in this equation number 3. Now putting the value of IB from the equation 1 in equation number 3, we will get VL is equals to V1 divided by A2 minus, in place of IB, I just substitute here IL minus IA into ZB. Call this as equation number 4. Now solving equation 2 and equation 4. Because these two are just equate these two equations. Equation number 2 and equation number 4 are equated. If you equate these two equations, then solve for what? IA. If you solve for IA, then you will get IA is equals to ZB IL divided by ZA plus ZB plus V1 into A2 minus A1 divided by A1 A2 ZA plus ZB. Similarly, you can write IB. How you can write IB? So here what you consider, this equation you consider. So here in place of IB you substituted the value from equation number 1, that is IB is equals to IL minus IA. Similarly, in order to obtain IB, so just consider the equation number 2. So in equation number 2, so just in place of IA, you just substitute the value from the equation number 1, that is IA is equals to IL minus IB. Substitute here in place of IA, IL minus IB. Then again solve this equation number 2 and equation number 4. Then you will get IB is equals to ZA IL divided by ZA plus ZB plus V1 into A2 minus A1 divided by A1 A2 ZA plus ZB. Call this as equation number 6. So this is the what? The secondary current of a transformer A, and this is the secondary current of what? Transformer B. See, these two currents has the what? Two component. One component is that the current sharing or load sharing between the two transformers. So this is ZB IL divided by ZA plus ZB. ZA IL divided by ZA plus ZB is the what? This is the what? The load sharing. So one more component is what? So this component is what? This is the circulating current. So circulating current at the secondary of transformers which are connected parallelly. So obviously this circulating current, it has some drawback. So we need to avoid this circulating current. What is the purpose? Why we need to avoid the circulating current? So what are the drawbacks? So that we'll see here. So you know the current IA and IB has the two components. The first component represent the transformer share the load current, and the second component of a is a what? Circulating current in the secondary winding of a single phase transformer. And this circulating current has what? The drawback. So what are the drawback? What it does? So there is an undesirable effect. So first effect is what? They increase the copper loss. The second effect is what? The circulating current overloads the one transformer and reduce the what? Permissible load KVA. So in order to avoid these effects, so we need to eliminate this circulating current. Then how to eliminate this circulating current? So this is what we consider here, the equal voltage ratio. So in order to eliminate circulating current, the voltage ratios must be what? Identical. So what here? What is the voltage ratio here? A1 be the what? the voltage ratio of what? The transformer A to be the what? Voltage ratio of the what? Transformer B. So these should be what? Equal. If these two will be equal under this condition, then IA and IB currents are written as IA is equals to ZB, IL divided by ZA plus ZB. Similarly, IB is equals to ZA, IL divided by ZA plus ZB. Call these equations as equation number 7 and equation number 8. Now here, so this is the equation, just I will repeat once again, because with this equation I supposed to write this equation. Since I just repeat once again, so equation number 7 and equation number 8. So here equating equation 7 and equation 8 we will get. So equate these two equations. If you equate these two equation, what happens? Or you can say equate these two equation, or you just take down your these two ratios, that is IA divided by IB. So divide equation 7 with equation number 8. So that is IA divided by IB is equals to ZB divided by ZA. So this is what common, that is IL divided by ZA plus ZB is the common. Here also IL divided by ZA plus ZB. So both are gets cancelled. So this becomes IA divided by IB is equals to ZB divided by ZA. Now from this equation you can observe that the current which is the load which is shared by the transformer A is equals to the reciprocal of what? Its impedance. What is its impedance? ZA with its impedance. That means IA is equals to what? IA is proportional to what? 1 divided by ZA. Similarly, IB is proportional to what? 1 divided by ZB. That means, so this is the one more condition for the parallel operation of a transformer. So if one transformer is supposed to share the load, in that case, so its impedance should be what? The reciprocal. So here also the IA is the what? The load shared by the water transformer A is proportional to what? It's the reciprocal of the water impedance, that is 1 divided by ZT. Now equation 9 can also be written as, so this can also be written as what? IAZA is equals to IBZB. So just bring this ZA into left hand side and bring this IB into what? Right hand side. So call this as equation number 10. Now the current in the equation 7 and 8 is changed into volt ampere by multiplying two equations by the what? Common voltage, that is VL. This is the common load voltage. So both sides you just multiply what? VL. So if you multiply both side VL, so this becomes what? Volt in case of what? Volt ampere. So where you will multiply? So both side VL. So here just multiply both side VL means what? So here where you will multiply both side VL. So the current in the equation 7 and 8 is changed into volt ampere by multiplying the two equations by the what? Common load voltage VL. So here also just multiply VL, here also just multiply VL. If you multiply VL here you also multiply VL here. So in general you can represent the total load in volt ampere is what? SL is equals to VL into IL. So this represents the what? The reactive component. Again just go for what? This part, that is for the transformer A. So for the transformer A, if you represent this in terms of volt ampere, so this becomes SA is equals to VL into IA. For the transformer B, that is to be represented into volt ampere, then you can represent S suffix B is equals to VL into IB. That means our intention is to what? So this can be represented in terms of what? Volt ampere, because our transformer rating we can represent in terms of what? The volt ampere. So since we'll consider, so these are what in terms of what? The volt ampere. Here by considering the equation number 7 and equation number 8, so we can represent the volt ampere rating of transformer A and transformer B as SA is equals to ZB divided by ZA plus ZB into SL. SB is equals to ZA divided by ZA plus ZB into SL. You just with respect to equation number 7 and equation number 8, just go for equation number 7 and equation number 8. So like that, so these equations are written, that is equation number L1 and equation number 12. Now again here, equating the equation number L1 and equation number 12, we will get as SA divided by SEB is equals to ZB divided by ZD. Either you can equate or divide equation number 1 with equation number L1 with equation number 12. That is SA divided by SB. So that is equals to what? ZB divided by what? ZA. These are the what common term. SL divided by ZA plus ZB are the what common terms. So these will get cancelled and this equation become SA divided by SB is equals to ZB divided by ZA. Now here also the volt ampere load on each single phase transformer is what? Inversely proportional to its impedance. See, if you consider the transformer A volt ampere load. So this is equals to what? The 1 by what? Impedance, its respective impedance, or you can say that what? The transformer A volt ampere load is inversely proportional to what? Its impedance. What is its impedance? That is ZA. Similarly, if you consider transformer B, the transformer B is volt ampere load is inversely proportional to what? Its impedance. Its impedance is what? Z suffix B. So this is also one more condition. So this condition is also what? Satisfied. So then only we'll go for what? The parallel operation of what? Transformers. Hence, to share the load in proportion to their rating, the transformer should have the what? Impedance which is inversely proportional to their rating. So this is one more condition. So this condition should be fulfilled. So then only we'll go for what? The parallel operation of what? Transformer. Now this is what regarding the parallel operation of transformer. So what is the necessity of parallel operation of transformer? And what are the conditions for parallel operation of transformer? Then, so those conditions are what? Proved here by considering the what? Two transformers, that is transformer A and transformer B are connected in parallel. So then we proved the some conditions of the parallel operation of what? Transformer. So this is about the parallel operation of transformer. In next video, we'll come up with some cases of the parallel operation of transformer. So what are those cases? So you are going to consider what? Either it may be what? The same transformer are to be considered parallelly, or different transformers are considered what? Parallel. Different transformer means what? The ratings are changed. If the identical transformers are connected parallelly, in that case, what conditions will get? What is the load sharing? So if the different transformers, different rating transformers are connected parallelly, then what is the load sharing? So that we'll discuss in next video. Until then, thank you.